In this video, I want to look at some of the things that can happen when you're trying to locate local maximums and minimums. And I think I'll just start with some simple examples and you'll see from them what can happen. In one case, you have a graph that has a nice, smooth local minimum, say, and that minimum occurs at C. This is the graph of F. Well, what's going to happen is as you come to C from the left, the y values, or you can follow the graph as you do it, you can see that if you pick any slope of a tangent line over here, every one of them will have a negative slope. But then as you approach C from the other side, you can see that these tangent lines, if you pick any one of them here, will always be positive. So what's going to happen is these lines will flatten out as you come from the left, and these lines will flatten out as you come from the right. So they're approaching from the negative side horizontal line. So this is a situation where f prime will be 0 at C. But what it'll do is, since it was the graph was decreasing, if you will, going down, we're going to have f prime is negative until you get to C. At that place it'll be 0, but then when it gets past there it'll be positive. So you'll see something like this occurring. Now this graph doesn't have to be a straight line. It can have other forms, but the fact is right before C it's negative, and right after C it is positive. Right, here's a graph that exhibits exactly the kind of behavior I was talking about here. F of x equals x minus 2 squared plus 3, and then f prime of x equals 2 times x minus 2. So you can see our lowest point here, our local minimum, I guess it would be an absolute minimum as well, occurs right at the bottom here at the point 2, 3. So that's a local and absolute minimum. But the important thing is that the function was decreasing before I got to 2, so the derivative is negative before I get to 2. Then it's increasing after 2, and the derivative is positive after 2. So in a situation like this, what you'll typically do is, you'll remember I set up those sign charts, and I would look to see if the sign of the derivative changed from negative to positive. If it did that, you had a local minimum. If it happened to go from positive to negative, then you would have a local maximum, because the thing would go like this: positive, 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 and then negative. So these are the easiest possible ones that we have to deal with. Many other cases will have situations where you have to do a little more work than just what's fairly obvious, and I'll show you those next. So another situation that can occur, you'll still have a local maximum or a local minimum. It'll be situations like this where you have like a sharp angle, something like that. A lot of times you'll see something like this with an absolute value function. But anyways, if this is the original function, the derivative will work like this. Let me put, once again, the highest C is where the point exists. If you look before C, I have a positive slope, and after C I have a negative slope. So this could be like positive 1/2, maybe this is negative 1/2, whatever it is. Here's what's going to happen. Since this is flat, a straight line, the derivative to the left of C is just the slope of that line. Since it's positive, you'll see something like this occur. And now on the other side, it's negative, you'll see something like this occur. You'll have a hole here because it won't exist at C. So you have a situation like this. You can see clearly the derivative doesn't exist here. It doesn't have a value here since the left-hand limit was different from the right-hand limit. Remember, the definition of a derivative involves limits, so you still have to make sure the left and right-hand limits are the same in order for it to exist. So a situation like this should lead you to believe, because you do still have, even though the derivative doesn't exist here, you still have a positive derivative and then a negative derivative. So you go from positive to negative as you go through C. That should tell you that you're going to meet at a point, because it's going from positive and then to negative. The only time you won't find this particular point this way is if that had been a hole up here at the top for some reason. But that rarely happens, so this is a situation that does occur sometimes. Okay, here's the real life situation here. The function that I've graphed is f of x equals the negative absolute value of x minus 2 plus 3, so it's similar to the last one. And you can see that I have a local maximum here and an absolute maximum at 2, 3. But look what the derivative does. F prime of x equals negative absolute value of x minus 2 divided by x minus 2. So as x comes in from the left, didn't mean to move that. As x comes in from the left, you have a positive slope. That corresponds to this here. But remember, while this program's not writing it, we have holes at the ends of those things. In fact, let me show you why this is the case here. But you can see this should tell you, since you go from positive to negative, that you're going to have a local maximum, and maybe even an absolute maximum in this case. Or just note, there are two ways to differentiate the absolute value function. You have two definitions of them. One of them is this one. The absolute value of x is the same as x if x is great. If x is not negative, then the absolute value of x is just x. If x happens to be negative, then in order to make it positive, you take its negative. This is the version that practically everybody sees. And then when you take the derivative of it, you simply take the derivative of each piece. This piece, the derivative of x is 1. Unfortunately, it will no longer be defined for 0, and negative 1. This indicates that it's not defined when x equals 0. This is nice, but I had to tell you about this greater than or equal to changing to just greater than when you take the derivative. The reasonings are complicated. I don't want to deal with it. There's another way of dealing with this. And a second form of the absolute value looks like this. The absolute value of x is the square root of x to the second power. Or better yet, x to the second to the 1/2. Now, I don't want to simplify it. That's the last thing I want to do. I want to take the derivative in this format because I have an inner function and an outer function. So when I take d over dx of x squared to the 1/2, the first thing I'm going to do is take this 1/2 in front. I'll get 1/2 x squared to the negative 1/2, and then I'll take the derivative of x squared because of the chain rule. So I'll get 1 over 2 times the square root of x squared times 2x. And then what I end up having is, notice that the 2's cancel. I'll have x over, and if I want to rewrite this again as the absolute value of x, to me this way is more evident that the function is not defined when x equals 0. So I like this. I like this way better. In fact, you have a formula for it. Let me put d over dx of the absolute value of x equals that, and that's something you can memorize. By the way, let me add one thing to it. This is also the same thing. Basically, all that happens is when x is positive, this number is 1. When x is negative, this number is negative 1. So, a sharp point That's one type of sharp point that can happen. There's a second type of sharp point that can happen, and it looks like this. You could come in here, be like a curved kind of a thing, and then you could curve up like this. Now this is different than the last kind, because while you do have a negative slope beforehand and a positive slope after the fact, these things are curving to become vertical. So you're actually going to have a vertical tangent line. A vertical tangent line and what's going to happen here then is these slopes are negative, 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 and they're going off to negative infinity. To the right, though, these slopes are positive. They're going positive, positive, positive to positive infinity. So if this is the original function, then the derivative, let me put this value at c, the derivative is going to have a vertical asymptote at c, and from the left, the derivative is going to go to negative infinity. I erred, completely erred there. Since the slope is negative on this side completely, that means I need to be below the x-axis completely. And then to the right of it, this, as you get closer and closer to c from the right, the slopes are becoming vertical, but positive. So you have something like this occur. So that would be f prime. All right, here's an example that shows the behavior I'm indicating here. This function, f of x, equals x minus 2 to the 2/3 plus 3. And even though the computer is not quite capable of showing this here, this point is actually supposed to be at 2, 3. Do you see it's off of there by a little bit? It should be right at 2, 3. I'm going to make it really big because that's where it should be. And based on calculus, you would be able to tell that. So there are some times you'll actually be able to get an answer that the computer is not able to get. The derivative, f prime of x, equals 2/3 x minus 2 to the negative 1/3 power. And since it's to the negative 1/3 power, this is really can be thought of as 1 over x minus 2 to the 1/3. And that's why we get a vertical asymptote here. And as you can see, to the left of 2, we got negative slopes going down to negative infinity, like I mentioned. To the right, positive slopes going up to infinity the closer they get to 2. It's hard for me to draw the dashed line in here without running into the graph, but I'll try to do the best I can. So that situation is also something where you should be able to tell what's going on based on a little bit of analysis. This here it's not going to be defined at that point, but you're going to see that you're going to go from negative to positive as you go through that value. So that had a local minimum at 2, 3. Local and global minimum. Another situation that can happen is where the graph comes and does something like this. It'll come in, but then it'll come and become vertical, like so. And then what will happen is, let's say this point right here is C. Now, in a situation like this, then you have a positive slope that is going to positive infinity, but then on the other side of it, the slope is also positive again. So you'll have a graph where you'll still have a vertical asymptote at C, except before and after the derivative was going to positive infinity. Now this is sort of a complicated one. It's not complicated in what happens. Certainly you should be able to tell if you get a situation like this, that something like this happens. If both of these are positive and the derivative is not existing, then the limit should have been the same, since it should have existed since it was the same on both sides. But the fact is, since it's going to infinity, you have a vertical tangent line, you do have a vertical tangent. If I were to draw a tangent line through here, it would be vertical. The problem with it is that it is not changing from positive to negative or from negative to positive. It's going from positive to positive. So that should tell you something, if it goes from positive to positive, that you do not have a local max or a local min. So no local extrema in this case. I'm hoping that you're not trying to memorize these cases, but this is just some of the things you should be aware of and use a little bit of analysis to determine what's going to happen. Okay, here's another one that exhibits what I'm trying to speak of. F of x equals x minus 2 to the 1/3 power plus 3. Here you can see that I have something going on here, but it's neither a max or a min. I'm increasing before and after it. So as I mentioned here, you have that vertical asymptote that occurs and no max or min. Perhaps the last sort of situation I can think of goes something like this. It's similar to what I just had, except you're going to have a derivative that is 0. You're going to have it come in, it's going to horizontal out for just a moment. Let's say that occurs at C. So you'll get f prime of C will be 0, but unfortunately you're positive before and after, or this could be flipped in negative before and after. And what's going to happen then is at C, you're going to get something that looks like this. So it's going to be positive before and after. Here's F. Here's F prime. And so this is not going to give you a max or min. So all these situations, you should be able to determine what's going on. No max or min. Here I have f of x equals x minus 1, x minus 2 to the 3rd plus 3, so that f prime of x equals 3 times x minus 2 squared. And I just noticed something that I did wrong in my picture here. The derivative's value is 0 right here, so this actually should come down and touch the axis. So that would have been a better graph of it. So you can see once again, the 0.23 is here. No local extrema. So what I've done in all of these cases here is run through all the possible things that can happen in what's called the first derivative test. The first derivative test encompasses all of these things. You basically look to see what the derivative is doing before and after a critical number. So when do you have critical numbers? Critical numbers occur where the derivative is undefined or where the derivative is 0. These are the two things that will set you off, and you'll start to look at all of those possibilities and examine them based on that. So the first derivative test encompasses all of this stuff. Your book gives a nice concise terminology for it, but you have to look at any of these possibilities can happen when you're dealing with the first derivative test. All right, and all these happen to have a situation where the function itself had no breaks in it. Every single situation here, the original graph had no breaks in it, but the derivative did sometimes, and that told you what to do sometimes, and other times you were told to do something else. It all depends on what your analysis is when you do the number line. So all of that encompasses the first derivative test. So we'll just say the first derivative test And that's that stuff. So let's move on to the second derivative test. What does that do for us? Now in this situation, there's some things to look for too. Let me go back to a situation where we have a local maximum, something like this, and C is where it's occurring. So let's say this is F. Then F prime, if this was a quadratic function, F prime would be linear. But whatever you're going to have is, before C, you have a positive slope, 0 at C, and then a negative slope. So it's going to go something like this. All right, then, what's going to happen when you take the derivative of this? Well, if this were a straight line, it has strictly a negative slope. So in a situation like this, we would have a graph that is perhaps maybe squiggly, but roughly straight. But the important thing is it's completely negative. It is negative around C. Let me put C's in all these places. What that means is the notion that goes with this says that the function is concave down at C. And you sort of get the idea. Concave is supposed to have the same kind of feeling of concavity that we have in everyday life. You know about convex and concave mirrors and windows and things like that. It's the same kind of thing. We say this is concave down if it looks like it opens downward, and I don't know how else to say it, but it's bowed downward like this. Or if you want another way to look at it, if you take any tangent line, any of them on this graph, any of them, the tangent line will be strictly above the graph at that particular point. Well, actually, a little wrong way. So in a way, the curve is bending away from its tangent line. Concave up would have it would still have a curve bending away from it, except the tangent lines would be under the graph in those cases. So a situation like this would occur, and this is a way of confirming that something is a local max or a local min without having to do the first derivative test. Say, let's just do an example to illustrate this. Suppose I have f of x equals negative x minus 2 squared plus 3. And this, of course, is going to have a local maximum at 2, 3, just like all the other ones that I invented. And I don't know, but the important thing is that it's concave down here. I'll show you how you tell what happens. When I take f prime, that's going to be negative 2 times x minus 2, which is a line. And it's going to have a 0 at 2, just like we figured it might be. Negative slope, so it's going to come in and do something like this. But then when I take the second derivative, that's going to equal just negative 2. So at negative 2, this is going to go through here and just constantly be negative 2. So if I didn't want to do this test, if instead I just went straight to this, then I know automatically that I have a local maximum because the function is concave down. If the derivative is 0 and the function is concave down, you don't have any choice but for the point to be at the highest point, so local maximum. That's the gist of the second derivative test. So let's take a look at what we have here. Let me just write in some detail what it is. Second derivative test looks like this. Let's start with, you have f prime of c equals 0. So the derivative exists. Now, that doesn't mean that f double prime has to exist, but if it does. Okay, so if f double prime of c exists, then f double prime of c greater than 0 implies concave up, which implies a local min. So keep that in mind. We usually write something like this. Concave up. That way you can see from the picture that whatever we discover here will be a local minimum. And then if you have f double prime of c is less than 0, this is concave down. And that means you'll have a local max. Second derivative is very, very simple. So you'll have a local max, something like that.